Hey everyone, hope you're having a good Pollinator Power Party, and thanks again for joining us for Pollinator Week. My name is Anthony Colangelo, and I'm the Communications Manager at Pollinator Partnership, and this is my field assistant Zelda, and we are calling from Yellowknife, Northwest Territories, Canada. We have a really exciting day planned for you today. We got Dr. Lars Chittka here, who is the author of The Mind of a Bee, and we also have artist Kadeen Navarro, who will be covering the sounds of seeds, which will all be super interesting. And we'll be covering some really cool questions such as can bees feel, can they play, can they be happy? So we'll be expanding the mind a little bit, and I'm really excited to see these presentations. And let us know what you think in the chat about those questions. And don't forget to tag us on social media using the hashtag #PowerandPollinators. And we hope you have the best final day of the party. So thanks so much and enjoy.
Today's obscure pollinator is the soldier beetle, Chaliognathus pennsylvanicus. Long ago, almost 20 million years before there were bees to pollinate so many of the plants which rely on, there were beetles. Magnolias, for example, are an ancient plant lineage that relied on beetles for pollination in the absence of bees and wasps. Today, many beetle-pollinated plants, like magnolias, have large, showy, fragrant, and cup-like flowers with leathery petals, which are a direct result of the plant strengthening itself for visiting beetles. A common North American beetle is a group called soldier beetles, or leatherwings, a beneficial insect and important pollinator who not only finds a good snack in the nectar and pollen of flowers, but also in other insect eggs and larvae. Soldier beetles survive through the winter as larvae, and then in the spring, they become active in leaf litter and plant debris, sometimes for up to 3 years. Then, in late summer, the adult soldier beetles visit many flowers, such as Queen Anne's lace, milkweed, rattlesnake master, solidalgo, and other late summer flowering plants. So, next time you find yourself in the garden, keep your eyes out for these resilient, bright yellow creatures visiting your flowers.
It's important that LADWP protect pollinators because we recognize that it's our responsibility as a public agency to fight climate change, to address the biodiversity crisis. Sustainability is a core part of our mission and how we provide reliable water and power service to our customers in an environmentally responsible way. Pollinators are vitally important. They're essential to creating and maintaining habitats that all creatures, including humans, need to survive. LADWP is already demonstrating leadership in this area, from tagging monarchs up in Bishop to planting pollinator demonstration gardens throughout our facilities. We actually even have a budding garden right here at Chatsworth Nature Preserve, thanks to our partners, which include the Santa Susana Mountain Park Association and Sky Valley Volunteers. We also have all of our landscape programs encouraging native plants, and we're partnering nationally through EPRI and the Power for Pollinators initiative.
Here at our Relic Steam Plant facility, we have one of the largest installations that consists of our nursery, our pond area, and also our pollinator garden. We have had the opportunity to plant different types of citrus trees, different types of fruit trees, a lot of vines on our fence area, and also a lot of succulents and cacti, and a lot of native plants as well. And because of it, we have a numerous amount of bees and hummingbirds, butterflies, and moths that have been coming around.
We brought in a lot of California natives that specifically draw bees, butterflies, and hummingbirds. And so a lot of the native salvia species, some of which we have here up on the plateau and in containers here in the nursery section are plants that are very attractive to bees because they produce a lot of nectar. Some of the larger flowered salvias, like the Salvia clevelandii, does draw hummingbirds. And you'll see on some of the plants that we have up there, we have the California bush poppy, Dendromicon, which has already, it's been blooming for several months, real pretty yellow flowers in the ranunculus family, and you'll see some seed pods already developing off of those flowers because they've been fertilized by pollinators. Native plants actually are fire adapted, so even a lot of the wildfires that are so destructive to us, a lot of times the plants will actually, especially in a year like this year with a lot of rain, will regenerate very quickly. And that's all because of the pollinators and what they do, spreading pollen from one plant to another so that the next crop of seeds can mature and regrow. The department actually has had for a number of years now a great program to incentivize homeowners to remove very thirsty lawns that use quite a lot of water and require a lot of regular upkeep to look manicured and nice all the time. The incentive that the department offers has made the difference for a lot of people between putting in more asphalt and cement versus putting in beautiful landscaping.
What's going on, Pollinator Week friends? My name is Michelle Dellinger. I am an environmental steward for vegetation management and First Energy, and we're excited to share with you some of our pollinator projects that we've been working on here this year.
Hi, I'm Keith Fuller with First Energy's new construction forestry team here in the Eastern Panhandle of West Virginia on a site that we completed early last spring and seeded early last summer. And what we were out here to do is clear an area for enhanced substation security. And what we decided to do was, instead of implementing our typical cool season grass mix, we wanted to compare and contrast the pollinator mix versus our cool season grass mix. And our results were very promising. So here we are in some of the plots that we planted out here. We have 25 plots. 5 of them are our cool season or turf grass plots. And then we have 20 of the native pollinator seed mix plots. And if you look behind me as we transition out, you could see a lot of the remnants from last year's growth, which is predominantly black-eyed Susan. And that is one of the early succession pollinators. They kind of come in, outcompete some of the other invasives, and shelter some of the longer growing pollinators to allow them to come up. So we'll see how it goes. So here I am starting in one of our native cool season turf plots. As I continue on, you'll notice there's a distinct changeover to one of our far more diverse pollinator plots. We have clovers, we have several pollinators that are just now starting to come up, and if you look close, we have several black-eyed Susans left over from last year that are hopefully going to keep coming up this year.
So another really interesting aspect of this project is working with Bat Conservation International. We've joined forces with them to determine whether or not bats have a preference in their foraging habits on our cool season turf mixes versus our pollinator seed mixes. So what they've done is they've put up several of these bat acoustic monitors, and thus far what we have found in just 1 year is that bats tend to prefer to forage in the cool season turf mixes, but it's still a newer project and there's more to come, so stay tuned on that one.
So this is a promising sign. Here we have some common milkweed, obviously a specimen from last year, but it's promising, it's on site, it's growing, and hopefully a good sign of things to come in the near future here. Thank you.
We're at the Flagstaff Arboretum. It's a pollinator festival event, and APS is the title sponsor.
The Flagstaff Arboretum is really about celebrating native plants and plant communities to the Colorado Plateau. This event is special to me because it's bringing the community out. We're coming together around an issue that's really important.
People think about flowers and pollinators as kind of like a pretty nice to have thing, but they're actually essential. They say 1 out of every 3 bites of food was brought to you thanks to the action of a pollinator.
It's exciting to have APS sponsor the event and participate and partner with us, because it really just shows that they are more than just power, that they are interested in investing in our community, that they're interested in conservation of pollinators, of habitat, of restoration, and so it's just a perfect fit.
At some of the landscaping that we do at substations, for example, to make it kind of fit into the community better and make it look good, we also want those plant species to be functional. A lot of areas, especially urban areas, the main wildlife is actually pollinators. There's a lot of urban pollinators, these small insects, they get around.
There's these organizations in our communities that we don't realize how invested they are in the environment and sustainability.
A lot of people are like, why is APS here? What does APS have to do with this? And I think just making that connection, like we talked about, like how we're involved in maintaining the habitat in Arizona, I think it kind of opens people's eyes a little bit to that work, and that is like my day job, is doing that environmental work. So.
And they have whole staff and whole departments full of people that are worried about the biology and the geology and the plants.
When I was going to school, I didn't know that a job like the one that I have existed. You can get a job, protecting the environment, like for a power company.
Hello, everybody. So I'm super excited today to share the ideas in my new book, The Mind of a Bee, with you. So I've spent the last few decades researching the strange perception of bees. You can see on the upper left here that bees can see ultraviolet light, which we can't. So they sometimes see patterns in flowers that are completely hidden to us. And I've looked also at the intelligence of bees, for example, their ability to count, as in this case, landmarks on their way from the hive to a feeding station. But surely it's still a big step from looking at perceptual worlds and intelligence to actually talking about the mind of an insect. So why do I now refer to the mind of a bee? So before we go deeper into this, it's important to think a little bit about what's important in the world of a bee. What might her mind be occupied with? And in this context, the first thing that we have to consider is that bees have to be careful shoppers in the flower supermarket. That is, in the flight range of any one nest or beehive, there might be several dozen different flower species, all differing in colors and scent and patterns and so on, but also in the quality of the products that they offer to the bees, that is, nectar or pollen. How much of each of these commodities is there in the flower, and this determines their quality. And of course, bees have to remember these colors that are linked to the best rewards, or odors or patterns and so on, and then focus their foraging efforts just on those flowers that they've experienced as the most rewarding. And we, in our laboratory experiments, just capitalize in a sense on the bee's unique ability to associate almost anything with sugary rewards. So what you can see on the right side is a bee about to land on a little platform that has a droplet of sugar water in front of an image of a human face. And if she does that a few times, she actually memorizes the appearance of that face, so that you can then do something like a crime witness test, where you present the bee with a variety of different images of faces and ask her to recognize the one that she's previously associated with reward. And actually, it turns out that they're very good at identifying the correct face. Now, we also test bees with some intelligence tests that traditionally have been reserved for primates and corvid birds, such as a string pulling task. So here we have 3 flowers, 3 artificial flowers that are hidden under a plexiglass table. And to get to the nectar droplet in the center of one of the flowers, the bee has to pull the string out. And here's the first bee we ever trained on this task. And you can see she lands exactly in the right place, not on top of the glass table to get to the flower, and pulls on the string to retrieve the reward in the end. And this is something that previously only classical icons of animal intelligence were thought to be able to solve. But here is the next step of animal intelligence in the world of bees. We have here paired an experienced bee marked with a red dot with another bee that is actually completely naive with respect to this task. And the experienced bee pulls out the string, and now they both drink the nectar. The naive individual just scrounging on the efforts of the experienced individual. But you do that several times, and the previously inexperienced bee will now start to pull a string by herself. And for now, we can just see that they're getting a bit antsy because they've drunk up the nectar. And the experienced bee, the red dotted one, now pulls out the next string. The other one is still faffing about by the old floor, thinking there might be some more. But then she runs over to the experienced bee again to help her finish the nectar droplet. But over time, that inexperienced bee will pull strings by herself. And if you do that multiple times with different members of the colony, you can see how the skill of string pulling that's never been mastered by a bee in their evolutionary history before spreads through the colony like a meme, so through a social media. So here we've arranged all individual bees of one colony in a circle. Each dot is one bee, and the individual at the top, the yellow 31, was the one that we trained first. And whenever a line forms between, that's when the two interacted, like in the video that you've just seen. And when a dot turns colored, that's when the target bee has learned the task as well. So you can now see a whole bunch of orange bees, and these have all learned the task from our yellow bee at the top. But there is now also a purple bee. And this is a third generation of learners, so to speak. This one has now not learned the task from the yellow bee, the first innovator, as we call it, but from one of the orange bees. And the skill in this colony continues to spread with several sequential sets of learners. But in the end, practically all of the individuals learn the technique. And this is, of course, a unique skill, a kind of culture that's special to that colony. Now here we've again made the task a bit more difficult. So the goal here is to move an unattached object, a kind of tool or a token if you wish, to a destination. So this bee has to roll the ball into the center, to this yellow ring, to get a reward. And she learns this just fine. But we've now again been interested in the question of how bees might be learning this from each other, except here we've played a little trick on the interaction between the trained bee and the inexperienced one. You can see there are 3 balls, each at a different distance to the target. And obviously, the best way of solving the task is just to move the closest ball. However, this experienced bee, the one in the center here, knows that that's not possible because she's learned that these 2 closer balls are actually glued down. So the ball that she invariably moves is the furthest one, is the one that's the greatest distance to the target. And once she's got it in the center, they both get a big dollop of sugar water. But the critical question now is, what will the observer do when she's left to her own devices? So she sees this 3 times. She has no own experience with rolling balls for rewards. And so let's now look at what she will do when she's by herself. The question is, will she ape the demonstrator? Will she just copy the actions and move the closest ball? Or will she basically just do the clever thing and roll the closest ball? And that's what she does. She spontaneously comes up with a better solution to the same task, which tells us that there's some sort of appreciation of the desired end state of the task rather than just a stupid copying of what the demonstrator did. Now, all of this is exploring intelligence, although in a special way. It's exploring whether bees can solve tasks by thinking rather than just by trial and error, for example. It's not simple learning and memory. These bees, for example, just spontaneously came up with a better solution without trial and error. The following learning experiment, however, made me think for the first time, about 15 years ago, about whether bees might have simple emotion-like states. And so one thing that bees have to watch out for in nature are these crab spiders that often lurk on and prey on flowers. They're well hidden, well camouflaged, as you can see in these photos. And we've taken that situation into the laboratory to ask if bees can learn to avoid these spider threats by using these life-sized plastic models of spiders that you can see here, paired with a kind of a pincer mechanism where the bee could be briefly held between soft sponge pads without being injured in any kind of way, to see if they might learn to avoid this. And here's a video of this task. Again, bear in mind that the bee is only briefly captured, but not actually injured in any kind of way. So now she lands on the wrong flower, and she gets captured by these clamps briefly, and then released. And it turns out that as a result of such perceived attempted predator attacks, even though the bee survives unscathed, they learn very well to avoid the spiders. But not only that, their whole demeanor changes so that they will scan every flower very carefully before landing, inspecting it to make sure it's safe. But moreover, and this was really surprising in a kind of psychological sense, the bees often displayed so-called false alarms. That is, they would scan a flower that was perfectly safe and then reject it as if they'd seen a ghost. They'd seen a threat or perceived a threat that wasn't there at all. And this to us looked, at least, well, somewhat flippantly speaking, a bit like a human post-traumatic stress disorder. But how might one more formally diagnose emotion-like states in animals? There's no formal proof in any animal, not your domestic dog or cat, but there are certain common sense tests that one can do and that in fact are done on domestic animals, including those kept by farmers, goats and sheep and so on, to see whether they're kept in conditions that are conducive to their well-being or not, as the case may be. And one test is based on the proverbial glass that can be either half full or half empty. So it's an ambiguous stimulus, 50% filled glass, that an optimist might judge as, oh, that's pretty good, there's still a lot in there, and be quite cheerful, whereas the pessimist might go, oh, it's already almost empty, and be all sad about it. And this approach, using ambiguous stimuli to ask animals how they respond to them, is also, of course, extendable to bees by the same logic that it's used for domestic animals. And so what we've done to adapt this paradigm to the world of bees is we have this little flight chamber where the bee can either find blue on the left, in which case there's always a reward, so blue here is a good thing, or green on the right, and in that case there's never a reward. And the bee learns this. And then after she's been exposed to this training, she always flies in a very straight path to the blue target. And if she knows that green is unrewarding, she'll fly about for minutes sometimes before she finally will say, okay, if there's nothing else forthcoming, I might as well try this, but only with a great deal of hesitation. So that's our good and bad. Green is the bad stimulus, so to speak, and blue the good one. And now what happens with the ambiguous stimulus? That's our glass 50% filled. And it turns out that the response of the bees to this ambiguous stimulus depends on what happened to the bee before the experiment even started. If we give the bees a little sugar droplet before the experiment as a surprise, where she's never experienced one before, she responds completely differently to that ambiguous stimulus than when she's not had this kind of extra reward. That's shown here on the left. So in black, we have the responses to the good stimulus, blue, very fast reaction, the bad stimulus, green, very slow reaction. But what happens with the ambiguous stimulus? Well, if the bee has not been given a surprise reward, she almost responds as if this was the bad stimulus. But if she's previously had a reward, she now judges this ambiguous stimulus, the same stimulus, as more likely rewarding and responds to it with much less hesitation. And it also turns out that this optimism-like response to the ambiguous stimulus is driven by dopamine, as it is in us. And so at least by the same criteria that were used for domestic animals, in this case, the bees responded in an optimism-like state. And so to sum this up, it appears that bees can solve solutions to kinds of intelligence tests by thinking rather than by trialing out different solutions, and solve them spontaneously. They also display object manipulation in a manner that's equivalent to at least the basic form of tool use, and can even improve on solutions that have been demonstrated to them spontaneously. And they also appear to attach at least simple emotional states to rewarding or penalizing situations. And these are, I think, key ingredients of a mind. And so if you've enjoyed this, then there is my new book about the minds of bees. Thank you very much for your attention.
Well, Dr. Chittka, we are so happy to have you here today. So we just saw your presentation that kind of describes some of the key aspects of your work. I actually had the chance to watch it a couple of times because I needed to digest it. And I created sort of a summary of what I understand of it, and was hoping I could show that to you, and then you can help us kind of understand this a little more for our audience.
That sounds good.
All right. Okay. So this question that we're kind of talking about here is, for me, it's kind of two parts. So one part of the question is whether bees are intelligent, whether they're smart. And then the second part of the question is, okay, how does that extrapolate maybe into how they feel and whether they have emotions? So I thought we'd start with sort of this first part first, about whether bees are smart and have intelligence. So I took your presentation that you just gave and kind of walked through it a little bit and summarized it here. So it seems that bees can change plans to match changing conditions, as you showed in kind of your supermarket of flowers. And bees will kind of scan the current landscape, which is constantly changing, blooming, and flowers dying. And they can go and kind of look around and say, here's where I want to go. And they go visit flowers. So this idea of sort of changing and dynamically responding to their conditions versus just being robots and doing the same thing every day. And you made the point that she has some ability for human facial recognition, that if you put nectar or something rewarding in front of different faces, she learns and can go to the human face that's associated with the nectar that she wants, right?
Yes, indeed. Mm-hmm.
That's kind of amazing in itself. So you sort of likened it, I think, to identifying your perpetrator when you put the line up and saying, hey, that's my person, and going there, right?
That's the kind of setup that we used, yes. So to start with flowers, as you say, the challenge for a bee is that the market, so to speak, is constantly changing. So there are these products out there, so to speak, plant species that advertise the rewards with colors and scents and so on. And bees learn to associate which signals, which colors are associated with the quality. But as you say, that market changes. So flowers come in and out of bloom. Sometimes an overly popular plant patch is depleted by lots of competitors, and then there's no more point in going there. So you have to resample the market and find out what's now the most rewarding. And honeybees especially also have the opportunity to find out about that inside the hive, because they communicate about locations of food sources. But key to all of this is assessing the rewards, the sugar solution and the pollen that's contained in the flowers, and to have to learn what is associated with these rewards. And bees are so flexible in this regard that indeed they can learn to associate even images of human faces with such rewards. And the setup we're using is very similar to the natural situation. We reward our bees, as do flowers, with little droplets of nectar or sugar solution. And the trick with the face recognition test is then, of course, once the bee has learned landing in front of one image, we then have to put that image somewhere else and offer several alternative faces. And then we ask, well, can you still find that particular face that you previously were rewarded? And indeed, bees are really good at that.
Huh. Okay. Well, that is really interesting that they can recognize human faces and differentiate them. So, okay, so then the next piece you kind of took us through is that she can use tools to solve problems. With the experiment that you showed us was pulling a string to get to the reward, right?
Indeed, or even rolling balls. So having an object that you have to move to a particular destination in the same way as, let's say, we have to put a coin in a vending machine in the right spot using the right object to get a particular object that we want to get out of it.
Okay, so doing a job, so I would, with the analogy, if we play that out, I think of it as you do a chore and then you get your allowance. So they're willing to work and use tools to get the job done. Okay. And use of tools, you mentioned use of tools is one of these sort of characteristics to kind of think about how intelligent something is. Right?
Indeed. So these kinds of string pulling tasks are a classic paradigm that people have tested the intelligence of primates and corvid birds with, and so on.
Okay.
And indeed, it's a task that in nature, these animals wouldn't encounter on a day-to-day basis. So there's some reason, or a rather obvious reason why bees have to be good at learning flower colors, is because they do that on an everyday basis. But these kinds of intelligence tests, like string pulling, are deliberately far removed from what the animal does on a daily basis to basically probe their flexibility at solving unusual tasks.
Okay, and then so then going further from that as well is that she can learn by watching her peers. So this was the string pulling experiment, right? Where she could learn by watching not just one peer, but then that would be translated or move through multiple generations of bees, right?
Indeed. So what we're testing there is a kind of culture or tradition-like phenomenon where you don't just innovate a technique by one individual that solves it first, but others copy it, and the technique then spreads through the population. And that's a bit reminiscent of what people have done in, again, the primate literature, where there might be certain techniques of using fishing for termites in some chimp populations, or others use certain techniques of opening nuts or washing potatoes before consuming them. And these techniques are subsequently copied and spread through a population and then become part of their cultural repertoire, a sort of population-specific behavior, not genetically determined, but learned, that's unique to one group of animals and not any others. And that's what we're testing with the bees there. So the idea is that we have one additional innovator. That's what we call that animal that solves the task first. And then it gets copied and spreads ultimately to all or most of the individuals in a population, and can even be retained over multiple sequential sets of learners. And that makes it a simple form of a behavioral tradition that distinguishes that colony that's learned the technique through observation from all other colonies that have not been exposed to this technique.
Huh. Wow. Okay. 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 So that takes a kind of learning by watching your peers, and then that you're saying generation over generation can become part of the new culture of that group. But also you mentioned that she can find better solutions than her peer. So maybe you have the original innovator in the room or in the experiment, but then you have a the newbie that's never seen anything, and that was your demonstration by taking the ball that's clearly closer to the center where the reward source is, and she comes in and she sees the peer taking these really far balls, and then she tries it and she's like, there's clearly a better solution. Why are you rolling these balls from miles away? Just take the one that's right next. So the ability to find a better solution is something that you've observed.
So there is some form of thinking there that allows the bee to find a better solution without trial and error, without trying all three balls and finding out, aha, this actually gets me to the target quicker.
Do you have personal viewpoint on whether bees have emotions? Are they sentient beings? Do they perceive and feel? Are they happy and sad?
Yeah, so just to first of all, I think I need to express the difficulty on diagnosing such mood-like states with formal scientific certainty. The only organism where we can really be certain about such things are us human beings, because we can give verbal reports of our emotions. In anything other than humans, whether these are dogs or chimps or indeed artificial intelligence systems, there's no smoking gun type proof where we can say, aha, now by this criterion we know for sure that this animal feels happy or sad or excited or and so on. It is very difficult because we don't have direct access to these kinds of mind states in anything other than humans. But what we can do is reason by analogy, and to the extent that we have behavioral as well as neural as well as hormonal data to assess a particular animal's state in a particular situation, then we're nudging the probability that it feels something in the direction of this being more probable. And so, for example, we can't, let's say if you have your dog is injured its paw, you can't actually measure its suffering or its pain. You can't even with certainty say that it feels pain. And I think this difficulty becomes even more apparent when you think about the fact that even human babies up until the 1990s were often operated on without anesthesia, because doctors thought that they don't feel anything. So they would say, well, yes, of course they scream and kick and so on, but that's all just reflexes. They don't actually sense anything. And so today this strikes us as ludicrous. And if you observe your dog and it's wincing and it's protecting its injured limb and subsequently avoiding the situation where it was injured, it seems obvious that presumably it experienced some suffering, but we still don't have a formal proof. It's just common sense that if you observe all of these things together, and you can also perhaps measure stress hormones and so on, then it becomes quite likely that the dog actually is in distress. And we're using the same kind of reasoning with our bees. We're looking at the question from a number of angles. So I think drawing all of these lines of evidence together makes it at least reasonably probable that there is a kind of sentience or a capacity to feel.
This could have some pretty serious ethical implications for how we manage landscapes that will have real economic consequences as well. Do you have thoughts about the complexity of that?
Yes, I agree that this work has ethical implications. I think, as you mentioned, of course, in the agricultural industry, insects, bees are killed and poisoned by the trillions through neonicotinoids and so on. And I think this is generally now on people's and politicians' radar to some extent, because we realize that we need pollinators. They're beneficial for us humans. And so there is at least some concern that we're harming animals that do a useful service for us. They pollinate our crops and our nice garden flowers and so on. But the argument there is one of utility. It's because it's one where we say we need to conserve these animals because they do something useful for us. But of course, beyond that, what this new work shows is that the process of dying from a pesticide, which often dissolves internal organs or paralyzes insects and so on, is, well, very likely also accompanied by states of distress and suffering that we need to sort of figure in when using such chemicals.
As a field biologist, a conservation biologist, and work that I've done, it makes me think a fair amount about how we do field studies and site surveys, and the typical netting and bull trapping and all of that for invertebrates is pretty standard practice, right? Makes you think about that further. If you're out there working to conserve the resources, how much do you really need to be sampling all the species and bringing them back to the lab? Well, Dr. Chittka, we really appreciate you joining us and sharing your perspective. It's an incredible career that you've had, and congratulations for all of your success and the impact that you're having. And can take decades to have things hit to a place that the rest of the world is aware of what you're doing, that you've been doing for 20 years. So congratulations on sharing all of your research and your new book. And we really appreciate all of the insights. Thank you.
Thank you very much for your kind words and your interest.
In 2014, I invented a way to see sound. I wanted to make visible two ideas that are very present in my work as an artist. That there is a much larger and mysterious world that is alive outside of our anthropocentric one, and that perhaps we need a language that goes beyond words and that includes the imagination in order to understand the creative act of being alive. To do this, I entered into dialogue with one of the most subtle yet critical forms of life on the planet, the seed. I was curious about the expression of nutrition, health, and life, all wrapped up within a tiny and efficient form. With purpose-built mics, a creative impulse, and tons of resilience, we were able to record the sound vibrations of 9 native Ohio prairie seeds. To see the sound of these seeds, I adapted a traditional Japanese marbling technique by swapping air for sound. The sound moves the ink and creates patterns. Once the patterns appear on the surface, I absorb them with paper, digitize them, and then incorporate them into large immersive installations where visitors can experience being part of a language made directly by seeds. It is a fragile process. I have to slow down, pay attention, and adapt my breath in order to capture this ephemeral alphabet created directly by the clicking sounds emanating from the dry seeds. The curious thing is that the shapes seem to be species-specific. Echinacea always seems to produce 4 outstretched arms, while dogbane keeps to regular concentric circles. Are the sounds and patterns communicating to other species nearby, or responding to moisture in the air? The recorded popping sounds give us an experience of the aliveness of the seeds. The art opens up new research about the sentience of the world through a subtle and gentle nudge towards beauty. This work continues to expand, from museums to classrooms, from farms to healing hearts. Through this creative gesture that mixes art and science, intuition and traditional wisdom, visibility is given to the gift-giving processes held within each seed. Gifts of reciprocity and beauty, healing and humility, nutrition and food source, community building and relationship. And when we listen carefully, it sounds like love.
Okay, so that's a wrap. Thank you so much for joining us for the Power Party this year. Thanks for sharing your stories, what you've been doing, and following along. We had a great time.
And keep it going throughout the year. You can keep using our hashtag and sharing. Yeah, we hope you learned and were inspired. Yeah, we'd love to hear from you. And don't forget, 2024 Pollinator Power Party. Thanks again to our sponsors. Shout out to you guys. You guys make it happen. Appreciate it.